Hello, good evening, students. Welcome you all for this session 4 on states of matter. Yeah, in previous sessions, we studied about gaseous matter, macro study, as well as micro study, right? And then in today's class, we will be learning about real gases. So, to just briefly recap whatever we have learned, in gas laws, we ended up in the conclusion with the ideal gas equation and then Dalton's law, in which we learned about partial pressures. The total pressure is sum of partial pressure, and then diffusion, effusion, and last class, that was on Wednesday, we learned about gas velocities, various types, right? As a conclusion to it, I can say that most probable velocity will be minimum, and then average velocity, and then RMS velocity, right? Yes. And then we learned about kinetic theory of gases, which is the basis for macro study as well as micro study, right? Yes. But um, there were few assumptions of kinetic theory of gases which we can understand very clearly that they were violating, right? And that will lead to real gases, which we will learn about in today's class, right? Yes, let's go ahead. Real gases. What are real gases? These are the gases which are observable. Ideal gas is what we study in textbooks and which obeys all the laws perfectly well, but real gases deviates from ideal gas. Right. For example, PV has to be constant at constant pressure. However, as at constant temperature. However, here you can see that these all gases um, will deviate from that ideal behavior, which should be constant PV with respect to P. Right. Yes. So to understand why it exactly deviates from ideal gas, let's look into kinetic theory of gases. I think we will get answer over there. Right. Ideal gas says that there is no force of attraction between the molecule of gas. Okay. Before going ahead, I'll just tell you the importance of real gas. There are few equation. Van der Waals equation sometimes directly comes. Okay, directly a question comes on Van der Waals equation. Yeah, which is real gas equation. So that part is very important. And then few terms like Boyle's temperature, critical pressure, critical volume. All of these are very important topics. Okay, so be attentive and learn very nicely these topics, and then you can go and revise. With this, gaseous states will be done. Okay, liquid state a little bit is there, but the gaseous state is over. Okay, yeah. So continuing ahead, ideal gas. In ideal gas, the few assumptions that we made in kinetic theory of gases were there is no force of attraction between the molecules of gas, right? That was one assumption. Okay, let's see whether it is really true or not. Okay, take any gas beginning with H2O. H2O, if you take that gas above 100 degrees Celsius, it will be gaseous in nature, right? But is it that there won't be any intermolecular force between molecules above 100 degrees Celsius? No, there is some intermolecular force between molecules, right? Which increases as you decrease the temperature. And at 100 degrees Celsius, there will be equilibrium. And if you go little below 100 degrees Celsius, the intermolecular force dominates thermal energy. Right? So intermolecular force is not zero. Here, as it is mentioning, no force of attraction. That's wrong. Okay, there is force of attraction. Okay, that will lead to the deviation of real gas from ideal gas. In reality, almost all the gases have intermolecular force. That's the reason liquefaction occurs, or gases turn into liquid, because there is some intermolecular force which becomes higher and higher as you decrease temperature. Got it? And then there is another assumption. What is that? Volume of the molecule of gas is negligible in comparison to the space occupied by the gas. Yeah, and I gave you example last class, right? 18 ml versus 22,400 ml. Remember? Yeah, same 1 mole of water is 18 ml, and 1 mole of H2O in vapor form will be 22,400 ml. Getting it? So this is the difference. Makes sense. So that's why it's very safe to assume that actual volume, that is somewhere around this number, will be very negligible in comparison to the total volume. Right. However, when you increase pressure to very high level, okay, let's say in a sample, you have certain vessel in which there is some gas, and from above you are putting a piston and you are applying pressure. Okay, when pressure becomes very high, obviously volume will become very low. When volume becomes very low, actual volume is anyway going to remain same. Molecule does not compress. The void space which is there, that will decrease, right? So that's why what will happen? More and more molecules will come nearer, as well as the uh, the empty space which is there is going to decrease. Because of this, the actual volume which we considered negligible now becomes more important factor. Okay, so that assumption that volume of actual volume of gas is negligible happens to be wrong at very high pressure or very low temperature. Clear? Yes. So that is the reason the real gas deviate from ideal gas. Okay. Real gases occupy volume and they exert force of attraction and repulsion. Repulsion when they are closer. So when you increase pressure to very high level, volume the molecules come nearer to each other and they repel. Okay. And when they are far apart, yes, they exert force of attraction, which we assume to be no, there is no force of attraction. Okay. Yes. So if this is the ideal gas, in first case, real gas 1, they will come more closer, and in real gas 2, they will go more apart. Okay. One is attraction, another one is repulsion. Yeah. Yes. Factors affecting deviation. Nature of the gas. In general, the most easily liquefiable gas and highly soluble gas show larger deviation. Right? One which is most easily liquefiable. That means they have more force of attraction. Right? Pressure. The deviation is more at high pressure. This we all know. Temperature. The deviation is more at low temperature. This is also quite obvious. Yeah. Then there is something called as compressibility factor. What is this compressibility factor? This is a parameter which is used to measure the deviation of real gas from ideal gas. Okay, so that's why you can see PV. PV means actual pressure or pressure in real case, volume in real case. In reality, what is the pressure experienced and what is the volume experienced by gas divided by nRT. nRT I can also say PV ideal. Right. In case of ideal, pressure into volume is nRT. Got it? Yes. So Z will be equal to PV real by PV ideal or actual PV by nRT. Got it? Yes. In case of ideal gas, PV real, PV ideal, both will be same. So it will be Z equal to 1. And when there is attractive force will decrease the volume. Since it decreases the actual volume or real volume, Z becomes less than 1. Got it? And when volume is greater than 1, when there is repulsion, okay? And I can also say there is volume of gas correction involved over here, okay? Yeah, repulsion or volume of gas correction involved, which makes um, the PV factor to be greater. Okay, so when there is repulsion or volume correction, the PV factor becomes greater, hence Z becomes greater than 1. Okay. Yes, about this volume correction and the attractive force, that correction we will look at. Okay. So Z less than 1 becomes when attractive force, and Z greater than 1, then volume of gas correction or the negative repulsion. Repulsion predominates. Fine. Yeah. So compressibility factor is not constant. It increases at high pressure and due to volume correction dominating. Okay. So when you increase the pressure, when you go on high pressure, what happens is volume correction comes into picture, right? Because of the actual volume which we have ignored, now we have to consider that. And because we consider that, the compressibility factor increases. Okay. Yes. And there is steepness, as you can see. In case of H2, it's a straight line. That means it constantly increases. Whereas in case of other gases, there is initially decrease and then increase. Initially decrease and then increase. Let us try to understand the reason for that. Okay, H2 always shows positive deviation. But what in case of um, others? Okay, in other cases, there is pressure correction term. Okay, pressure correction term involved, which initially decreases the uh, Z factor. As you can see here, this graph is between Z and pressure. So at moderate pressure, at low pressure, we need not to worry so much about deviation from ideal gas. Real gas will behave as ideal gas at low pressure, okay, as well as at high temperature. Know this very nicely. Okay, at low pressure, molecules are randomly moving here, there is no pressure, so it will behave like an ideal gas only. However, when you increase the pressure or decrease the temperature, okay, then this deviation begins. Okay, at moderate pressure, you can know this, that pressure correction is dominating. How we will understand it now? And at high pressure, volume correction is predominant. Got it? Yes. Because of volume correction, the compressibility factor increases. Because of pressure correction, the compressibility factor decreases. Okay. Yes. So pressure measured would be less than the ideal pressure. That's why compressibility factor becomes less than 1. Okay. Why is that so? Because there is some attractive force. Okay. So we kinetic theory helped us to understand the pressure, right? So if there is a molecule, it just moves here and there randomly, and when they hit the walls of container, that is the cause of pressure. But molecules, when they are attracted to each other in some sense, the hitting of wall will not be with so much force, right? So that's why pressure will be less. Got it? So pressure will be less. Pressure real will be less. Yeah. So to make it equal to the ideal one, I have to add this factor. This is called as pressure correction term. P plus n square A by V square will give me ideal, in ideal case, what would have been the pressure. Okay. So ideal pressure is P plus n square A by V square. When this happens at moderate pressure. Okay. About this, we'll again come back. Then there is E is van der Waals constant, of course. Van der Waals constant means some force of attraction is there, right? For each molecules, it will be different. So there is that parameter is van der Waals constant, and value of A is measure of magnitude of intermolecular force, as I told, and it depends on nature of gas and is independent of temperature and pressure. So that means for every type of gas, A will be same. For every type of gas, A will be different. However, at various pressure range and temperature range, A will be almost same. Sometimes it differs a bit, but otherwise A will remain constant throughout. Okay, that is one drawback of this value A. Okay, because it deviates a bit. Yes, higher A value would mean more attraction, intermolecular force. Generally, for noble gases, A would be very small because noble means they are separate. They don't have any force of attraction. Clear? Yes. So that's why hydrogen and helium, they will not show that a ditch. Okay, in the Z curve, Z versus P graph, they don't show ditch because they don't have they have very less intermolecular force of attraction. A is very less. Okay, so because of pressure, deviation will be negligible. Got it? Next, let us understand about volume correction. So as you all know that when pressure becomes very high, the actual volume which was negligible previously now becomes considerable. So in case of ideal, the volume will be full volume. Whereas in case of reality, this volume has to be subtracted. And that we subtract using a factor called as NB. Okay. Total excluded volume for 1 mole of gas is denoted by co-volume B. And what is that co-volume B? It's van der Waals volume constant, and its value is 4 into actual volume of gas molecules. Okay, it's 4 times actual volume of gas. This volume, it becomes 4 times because the interaction between molecules increases the volume range. Okay, the radius, which is 1r, but when two molecules come, it becomes 2r. Okay, the volume, the radius becomes 2r, and that will lead to increase in the actual volume, which is not just V, it is 4 times V. Got it? Yes, and this is also constant per mole at per mole for every gas. Okay, because volume of gas, any type of gas will be same. So 4 times volume will also be same, no matter what pressure, what temperature you give. However, for different gas, it will be different. Okay. Yes. Next is ideal volume. Ideal volume is V minus NB, right? Because in reality, volume considered should be okay. Yeah. Yeah. To make my real volume in comparison to ideal volume, I have to subtract the actual volume factor. Right? Then only it will become equal to the ideal volume. Okay. So yes, there is a decrease. The NB factor has to be removed, right? Because actual volume is now not negligible. We have to consider the effect of that. That is the place where we cannot compress, right? Only empty space has to be considered. So to consider empty space, we have to subtract NB. Okay. Yes. So now let us look at various, first let us go into this real gas equation, which is pressure correction factor included in pressure and volume correction factor included in volume, which becomes P plus N square A by V square into V minus NB equal to NR. For 1 mole, it will be P plus A by V square into V minus B equal to RT, where pressure correction is N square A by V square and A is PV square by N square. This also has constant values, which I will just show. V equal to NB or B equal to V by N. Yes, and one more thing, students, questions may come from this van der Waals equation. So this equation is very important. Okay, so I sometimes B value they may not give you, they may ask you to find. So then you have to use B equal to 4 times volume of gas molecule. Let's tell H2O radius is 1 angstrom. Yeah, then you have to find out volume by 4 by 3 pi r cube into 4. Understood? That's how you will find out B, and most of the time B value will be given, A value will be given. Okay, you have to just substitute everything properly and get the answer. That's all. Okay. However, this equation you should remember. Fine. As here are various A and B values. For helium, it's least, as I said, because it is noble gas. Yeah, neon also it is less. Hydrogen also it is less. For other gases like N2, O2, Cl2, it's high because they have some intermolecular force of attraction. Okay. B value again it's different for different molecules and it's dependent upon their size. Right. Yes, and now let us look at various conditions. What exactly happens because of which the real gas deviates from ideal gas? Okay. Here we are only looking at high temperature condition. Okay, low pressure, high temperature, extremely high pressure. Again, temperature is moderately high, moderate pressure, and high temperature. Why we are not considering low temperature? At low temperature, uh, uh, obviously, real gas will deviate from ideal gas. Remember, I had in the beginning I had told two conditions which will make sure that real gas will deviate from ideal gas. When pressure is very high, when temperature is very low. These are the two conditions in which real gas or in reality gas will deviate from ideal gas. Got it? So that's why I'm not considering low temperature case because the number of factors will increase. Instead, when I consider only high temperature, the only factor will remain is pressure. If pressure is low, how will the real gas behave? If pressure is moderate, how will it behave? And if it is very high, how will it behave? Okay. Yes. Hydrogen and helium, why it is exception? That I have already explained a bit. Still, we will look into it. Okay. So at low pressure and high temperature, pressure is low and temperature is sufficiently high. So since pressure is low, volume or empty space is considerably high. I need not to consider this factor. Right? Yes. Low pressure and high temperature would mean V is very, very high. Volume is very, very high because temperature is high. Volume is directly proportional to temperature. So it will be high and also pressure is low. So volume will again be high. Okay. Yes. So I can ignore NP factor. And since pressure is very low, the AN square by V square factor, that also can be ignored because temperature is very high and at high temperature the attraction will be less, right? And also there is no pressure. When there is pressure, the molecules will be near to each other and then there is some chances of attraction, right? Now when the molecules are very far, the chances of attraction are very less. So that's why n square a by b square becomes ignorable factor. Okay. Yes. So the equation turns out to be ideal gas equation. PV equal to NR. Okay. And Z will be equal to 1 because it is now ideal gas situation. However, when the pressure is very high, extremely high pressure, in that case, what happens? Extremely high pressure, volume will be considerably low. So NP factor becomes prominent, right? Why it becomes prominent? Now volume is very low. That means empty space has become very low. So then we have to consider actual volume, right? And then what about AN square by V square factor? Yes, this also exists. This also exists. However, this correction predominates this. Got it? Yes. So extremely high pressure. So the pressure correction term can be neglected, right? Because pressure is very high. So N square A by V square factor, however big it may be, it will be low comparison to pressure. So I can ignore it, right? Yes. So what is remaining is only NB. So if I multiply PV minus PNB, P into V minus PNB equal to nRT, or I can move PNB to the other side and I can say PV equal to nRT plus PNB. So nRT I can divide and I can say PV by nRT, that is Z, equal to nRT by nRT, which is 1 plus PNB by nRT, which is PB by RT. So this makes sure that Z is greater than 1. That's the reason. Okay. So there is volume correction. The B factor comes into picture because of which compressibility factor increases and it becomes greater than. Got it? Yes. However, n square a by b square becomes negligible and it becomes only considerate at moderate pressure and high temperature. At moderate pressure, what happens? N square a by b square is comparable to pressure, right? So we cannot ignore it. We have to consider it. Whereas NB becomes prominent only at very high pressure, where volume becomes low and NB becomes prominent. Right. So we can ignore NB factor and we can only consider AN square by V square. Okay. So then the equation becomes PV plus AN square by V upon multiplying this with V equal to nRT. Or I can move AN square by V to the other side. So it will be PV equal to nRT minus AN square by V and divide whole thing by nRT. So it will be Z equal to 1 minus AN by VRT. So this because of this factor, Z now becomes less than 1. Okay, so there is some force of attraction which makes Z less than 1. Okay. However, when A is very low, in case of hydrogen, helium, neon, and other noble gases also, since A is less than very much less, so 1 minus that factor will become very less. So Z will become approximately 1. So that means the gases will tend to behave almost like ideal gas and the only factor remain for their increase will be NB. So that's why there will be gradual increase throughout and at very high pressure the increase will be very high because now NB factor has become very much prominent. Got it? Yes, that's in case of hydrogen, helium, neon and other noble gas. Yeah. Yes. So to conclude, low pressure and high temperature, Z equal to 1. At moderate pressure and high temperature, Z equal to 1 minus AN by VRT. So that's why you can see that this gas, this gas, this gas, all of them are having less than 1 Z value. Okay, 0 0.8, 0 0.6, 0 0.4, like that. And at extremely high pressure, you can see that all are having Z greater than 1. Why? Because of this PB by RT, that is volume correction. Okay. Yes. So hope this understanding is very clear. Fine. Yes, as I discussed that in case of hydrogen and helium, molecular mass is small, hence value of A is will be small owing to small intermolecular force. Okay. So they have very small intermolecular force. So AN square by V square will not be there, only NP will be dominating even at moderate pressure. Okay. Yes. What are the limitations? Let's look into that. This equation shows appreciable deviations at too low temperature or too high pressure. Yes, because A and B will not be same. It will differ a bit. B will remain same, however, A will differ a bit. The values of van der Waals constant A and B do not remain constant over the entire range of temperature and pressure. Hence, this equation is valid only over specific range of temperature and pressure. Same thing. Okay. So at too low temperature and too high temperature, we cannot apply this. Fine. Yes. Yeah. Try to answer this question. For a real gas, Z shows less than 1. Gas is less compressible. Z equal to infinity. For an ideal gas, Z greater than 1. Gas is more compressible. PV is not equal to nRT for real gas. Which one is correct among this? Which one is correct? Which one is correct? Yes, anyone? Yes. Which one is correct? Quick. Yes. Yeah, obviously, right? PV not equal to nRT for real gas. So option D is correct. However, I want to explain this also, that Z less than 1, gas is less compressible. No, gas is more compressible. Okay. And Z greater than 1, gas, yeah, it's true. Z is less than 1, gas is less compressible. Z greater than 1, gas is more compressible. Okay. So whenever Z is greater, we tell it is more compressible. Whenever it is lesser, we tell it is less compressible. But however, we cannot say for real gas Z will be less than 1 or Z is greater than 1. Right? And Z equal to infinity, that's not true for ideal gas. Right? So the answer is PV not equal to nRT for real gas. Yes, then there are few other terminologies and a few other characteristics of gases. Let us try to understand that. There is some temperature called as Boyle's temperature. So, as I said, at low temperature, deviation of a real gas will take place with respect to ideal gas. However, when you increase temperature, as you are increasing temperature, deviation reduces, right? So, as you are increasing temperature, the molecules are now gaining sufficient thermal energy. So, the force of attraction becomes very much negligible. And at one particular temperature, the thermal energy becomes so powerful that even if molecules are very near, they won't be um, um, having this force of attraction. Okay, so that temperature at which a real gas exhibits ideal behavior for considerable range of pressure is called Boyle's temperature. So yeah, TB equal to A by RB. That is the expression for Boyle's temperature. Okay. Boyle's temperature is that temperature at which it behaves or it obeys Boyle's law. The gas obeys Boyle's law. Okay. The temperature above which. Right? Yes, inversion temperature is the temperature at which no heating or cooling of gas can occur, and it is given as Ti equal to 2A by RB. Okay, so as you go above, as the altitude increases, temperature decreases. Okay, as you go above and above, temperature decreases, and the air, the gas which is there, that goes on decreases with its temperature. Right. However, density is higher at lower level and density is lower at higher altitude. So what happens? These gas molecules go above. So there are two things. The gas molecules which are at lower level tend to go up to lower density region, as well as the molecules which are there above are having low temperature, and because of these molecules which are at lower level want to go up, they will tend to increase the temperature of the upper layer. Okay, and at one particular time what happens, the motion, the molecules movement towards upper layers will become such high that the temperature inversion will take place. Okay, the temperature at which this inversion does not take place, okay, that temperature is called as inversion temperature. And above this temperature, if the lower layer is, then the movement is the movement will anyway remain same. However, the molecules go there and increase temperature to such an extent that inversion of temperature will take place. So that phenomena is called as inversion of temperature. Okay. Yes, and the expression is given for that is 2A by RB. Okay. So the point to note down over here is that inversion temperature inversion is twice of Boyle's temperature. Okay. So Boyle's temperature and inversion temperature are related as Ti equal to 2Tb. Okay. This is one thing that you should be knowing. How exactly that inversion temperature, that you may not remember. Okay. But what exactly is inversion temperature? No need. But what is the relation between inversion temperature and Boyle's temperature, and what is that equation that you can learn? 2A by RB, and Boyle's temperature is A by RB. Yeah. Yes. Since TB is A by RB, so Ti is 2A by RB. So I can say Ti is 2 times TB. Right? Yes. So Yeah. Next, let us just look into van der Waals constant application, that is liquefaction of gases. Okay. What is liquefaction of gases? It's a conversion of gas into liquid state when you increase pressure and decrease temperature. Right. So, as you go on increasing pressure at any particular temperature, the gaseous phase tend to go to liquid phase. And as you go on increasing temperature, the point at which gaseous phase will turn into liquid phase, that also goes on increases. Or in other words, at lower temperature, the at lower temperature, molecules tend to be in liquid state. At higher temperature, molecules tend to be in gaseous phase. Okay. Yes. So what is liquefaction? It is a physical phenomena of changing of state from gas to liquid. It can occur only when the intermolecular force of attraction are very high. Okay. The density of gas is same in gaseous point and yeah, as in liquid phase. That point is called as critical point, which I had discussed previously. Right. Critical point is the point at which the density of gas remains same both in liquid as well as in gaseous phase. Okay. Yes. But what happens above critical point? Above critical point, that means if you go above critical temperature, let's say this is TC, if you go above critical temperature, there is no chance of converting gaseous phase into liquid phase. Understood? So, how much ever you bring molecules closer, there won't be any attraction between the molecules. So, that's why they don't get converted to liquid. That temperature is called as critical temperature, and that point is called as critical point. Clear? Yes. If the value of A is high, gases can be easily liquefied, right? Because A is high means intermolecular force of attraction is high. Yeah. And a few terms related to liquefaction of gases is critical temperature. It may be defined as the temperature above which no gas can be liquefied, right? That's what we discussed. Critical point is the point above which if you try to increase the temperature, that will not lead to liquefaction of gases. What is liquefaction? Change of phase from gaseous to liquid, either by increase of pressure, decrease in temperature, right? Critical temperature TC of some gases are 5.4, 33.2, 126 for nitrogen, carbon monoxide 134.4, oxygen 154.3, carbon dioxide 304.1, ammonia 405.5. This is just for your information. Need not to remember all of this. However, this equation is very important. TC is related to A and RB or B, okay, which is 8A by 27 RB. Okay. Or else, in other words, I can say if van der Waals force of attraction, intermolecular force of attraction is high, A is high, critical temperature is high. Okay. Yeah. And if B is low or B is, yeah, if B is low, that means the actual volume is low, then critical temperature is high. Okay. Yes. Or the expression is 8A by 27 RB. Higher critical temperature would mean the gas can be easily liquefied or it has strong intermolecular forces. Understood? So since intermolecular forces is strong, critical temperature is higher. Got it? Yes. Then there is critical pressure, the pressure at critical point. Yeah, the pressure corresponding to critical temperature is critical pressure. At critical temperature, the pressure needed to liquefy the gas is known as critical pressure, which is given by A by 27 B square. This is also important expression. Then critical volume VC, the volume occupied by 1 mole of a gas at critical temperature and critical pressure, is known as critical volume, which is given as 3 times B. Yeah. Yes. So TC, PC, and BC is a constant value for every gas, and it is given here. You need not to know this, but just for your understanding, this is. Yeah. For few gases like helium, it is very low critical temperature. That means they have very low intermolecular force of interaction. Yeah. Critical compressibility factor. This is also something very important. Critical compressibility factor will be 3 by 8 or will be equal to PCVC by RTC. Okay. Yes. Let's go to this question. Critical temperature of ammonia and carbon dioxide are 405.5 Kelvin and 304.1 Kelvin respectively. Which of this gas will easily liquefy or liquefy first when you start cooling from 500 Kelvin to their critical temperature? Which one will liquefy first? Yes? Yeah. Which one will liquefy first? So we know that higher the critical temperature, higher intermolecular force of attraction. So as and when you are decreasing the temperature, the chances of liquefaction increases. However, one which has higher critical temperature will liquefy first, right? Because they have more intermolecular. Ammonia will liquefy first because its critical temperature will be reached first, right? Yes. The next question, critical temperature for carbon dioxide and methane is 31.1 degrees Celsius and minus 81.9 degrees Celsius respectively. Which of this has stronger intermolecular forces and why? Yes, quite obvious, right? First one, 31.1 degrees Celsius, right? Because A will be higher when TC will be higher. So TC is 31.1, that is higher compared to minus 81.9. However, this critical temperature is in Kelvin. This is in Kelvin. Now, since it is only comparison, I'm comparing 31.1, which is obviously greater, and hence A will be greater, and then that's why answer will be carbon dioxide. Okay. Next question, TC and PC of a gas are 400 Kelvin and 41 atms respectively. Then VC is, yes, just think over this is where you have to apply the formula that I had told. Okay, the formula of TC, PC and VC, or if not, then you can also remember PC VC equal to dash RC R into TC. If you know that, that's also solution. Yes. Yes. Any answer? Any answer? Any answer, students? Yes. What was the compressibility factors in case of in terms of PC, VC and TC? It's PC, VC by R TC, which is 3 by 8. Isn't it? So let us put that. PC, VC equal to 3 by 8 RTC. Yes. So what is given? PC is given as 41 atms. VC, they have asked us to find 3 by 8 RTC is 400 Kelvin. So if I put everything, VC will be 3 by 8 into R into TC, which is 400 Kelvin divided by PC, right? So PC is what? 41 atms. So 400 by 51. So 8 ones are 50, then 3 into 50, 150 R by 41. Right. So it is 150 R by 50. Answer is option 2. Clear. So this kind of questions are expected. So to summarize, we learned about real gas, how it deviates. Right. There the important things are compressibility factor, which is PV real by PV ideal, or you can say PV by nRT. Right. And then we studied that how it behaves at low temperature, at high temperature in various instances, at low pressure how it behaves in case of high temperature, at moderate pressure how it behaves, and at high pressure how it behaves, right? So to conclude, I can say that at low pressure all gases behave almost similar to ideal gas, because n square a by v square factor will be negligible, also nb factor will be negligible. Fine. And then as in when I increase the pressure, when we come to moderate pressure, the intermolecular force factor A becomes prominent, because of which there is a decrease in Z value. Z becomes less than 1, right? So that's why it will be 1 minus some factor of A. Right. And at high pressure, the NB factor or volume correction factor comes into picture, because pressure is very high, volume becomes very low. So we have to give some volume correction, and that will lead to increase in the compressibility factor. So for real gas, Z will be equal to 1 at low pressure, high temperature. Z will be less than 1 at moderate pressure and high temperature. And Z will be greater than 1 at high pressure and high temperature. Right. And then we learned about liquefaction of gas, and also we learned Boyle's temperature, inversion temperature, right? And then critical temperature, critical pressure, critical volume. The expression for them are very important. And also van der Waals expression, which is P plus n square A by V square into V minus Nb equal to nRT. And we learned that B is 4 times volume of one gas particle, 1 mole of gas molecule. Okay. And then yes, we learned critical pressure, critical volume, critical temperature, and we understood that compressibility factor, when we consider in terms of critical pressure, critical volume, and critical temperature, it will be 3 by 8. So PCVC by RTC is equal to 3 by 8. Okay. Hope you understood this whole thing. Okay. Real gas has some weightage. In competitive exam, questions are expected equally from both ideal gas and real gas. However, you can see in ideal gas, you spent around 3 hours. In real gas, you spent only 1 hour. So it becomes very important. Only small topic, but questions are expected. Okay, fine. Hope you understood this part of the topic. Thank you.